Hello, welcome to this video on the more formal notes on magnetism. And the first idea that I wanted to talk about was something you probably already know, but it's not very often mentioned. It is that the magnetism on a permanent magnet, it's concentrated at its ends, so we call this the pole. So what that means, it's pretty easy to know what that means if we just draw a magnet like this, right? This is always what we expect, that the magnetism is concentrated at the ends. So in other words, the lines, magnetic lines, are densest. They are the densest at the ends of the magnet. But this is also true if it's a longer magnet, right? If it's a magnet this long, then if it's the North Pole and it's the South Pole, then the magnetism is concentrated here in the ends also. So the field is strongest at the ends. And we call the ends the poles. So that was really the first idea that I wanted to talk about. Now let's look at the second idea. The second idea is that if you have imagine that we have some kind of base like this, and on top of the base we put a pin, and then we put a magnet that we suspend on top like this, and it's got an axis, it's got a little hole through the middle, and so it can spin one way or the other, and we're looking at it from the side. And if we looked at it from on top, if that was the magnet, and we look at it from on top, then this is gonna be if this was free to spin in this direction or the other direction, then the freely suspended permanent magnet will always come to rest in a north-south direction. So if there is a magnetic field in which the magnet is located, then this will always end up being at rest when it reaches an alignment with the north-south direction. So it's either going to align like that or it's going to align like that, depending if the north is in one direction or the other. Okay, so in other words, if it's not aligned, if it's at some angle to the north-south direction, there will always be some kind of turning force that will make it eventually fall at rest when it's aligned with the line of the north-south. Okay, hopefully that idea makes sense. So we can, you should be taking notes of these things in your own way, but I'll write them out in sentences after I've kind of illustrated them. So the second idea is that a permanent magnet suspended at its center, so a permanent magnet suspended at its center or free to turn will come to rest in a north-south direction. Right, if it's a freely suspended permanent magnet. So you can put this in brackets or whatever, if free to turn. Okay, and that's the position in which it will offer the least resistance, or the most stable energetic position for the magnet will be that. So things always tend to tend to the most stable energetic position, so that would be the one for a permanent magnet. The north-south direction. And how will it point? Well, you already know that north is attracted to south and south is attracted to north. So if this can spin and is completely free to spin, then if this is the north and that's the south, then if there is a north pole over here, then the north will be repelled from that north, and this will spin around. Right, this will just spin around like that until it looks like a south there and the north here, right? And then, so in other words, the south is the north-seeking pole, yeah, and the north is the south-seeking pole. So you can write it out in a not sure why it rubs those first. Apologies for that. So in a sentence it would be like saying that the end pointing north is the north-seeking pole. In other words, the south pole of the magnet. And this could be a little bit counterintuitive. I'll go into why that could be the case in a sec. So the end pointing south is the, I should have written here, is the north seeking pole, that should be there. Here is the south seeking pole, and that would mean that it is the North Pole. Okay, so what I'm saying there is that the North Pole of a permanent magnet is going to seek the south, therefore it's going to point towards the south, and the South Pole of a permanent magnet is going to seek the north, so it's going to point north. Okay, so when we have a magnet in our house and we look at the magnet and the magnet falls like that and it's pointing north, and if this is the north part of the magnet and that's the south, we normally call this north because the north points in that direction, right? But in the Earth gravitational field, actually, if the north points in that direction, it means that it's not the North Pole, it's actually the South Pole. So the geographical north is actually the South Pole, and the geographical south is actually the North Pole. Hopefully that makes sense. And really, ultimately, it doesn't really matter that much because these are all conventions. We invented what north and south was, so it doesn't make a huge difference. But it's just interesting to know that as far as the magnet that the Earth is, because of its rotating magma in the middle and all sorts of effects you have there, the magnet that the planet Earth is actually has a North Pole where it has a geographic south, and it has a South Pole where it has a geographic north. Let's see what number 4 is. Okay, if we wanted to show whether some material is a magnet, all you have to do is you come up with the North Pole of some magnet and you get it close to the material, and then if this is magnetized, then it will either be attracted or repelled, right? If it's repelled, then you know that this is North Pole, and if it is attracted, then you know that this is the South Pole. So you can always check by bringing a magnet next to the other, or next to the material that you want to test. So you can write this as to show if a material is a magnet, you can you can bring a permanent magnet North Pole or South Pole, it doesn't matter as long as you know what it is. North Pole close to it, and observe the effects. So this is pretty obvious, but it's still something that you could be asked. And observed the effects. Okay. And the last thing that I wanted you in this group of things to know, the last thing I wanted you to know is that the meaning of this phrase, which is a bit of terminology, if they tell you that something is magnetically saturated, it means you cannot make the magnet any stronger than it is. So you cannot make the magnet any stronger. Okay, so that's the meaning of magnetically saturated. Okay, so I'm going to talk next a little bit about induced magnetism and the meaning of that. So I'm going to write the title here: Induced Magnetism. So we can say that we can say that materials such as iron or steel, so iron or steel, they are attracted to permanent magnets. And this is because they become magnetized. So this is because they become magnetized. So in other words, the magnetic field of the permanent magnet, if this is a permanent magnet, then the magnetic field that gets created around here, which goes from north to south outside of the magnet, like that. Inside it goes from south to north. This magnetic field has an effect on anything you bring next to it, which is made of iron or steel. So if you come along with some drawing pins or something like that, then this will induce, so say you have a pin like that, and then here comes another one, and then another one. These three pins, if they are made of steel or iron, then if this is a south pole, then this part of the pin will turn into a north pole, and this one into a south pole, and then this one will alternatively do the opposite, and then this one like that again. So in the presence of magnetic field, you can't see all the field because I've only drawn two of the lines, but this would be right all the way over here. So they would affect anything in the vicinity. So in the presence of magnetic field like that, then any material like iron or steel will become magnetized, and then you'll create some extra poles here in the other north-south, and then here you would have a north-south, right? So these are, you could call them, if you want, yeah, you call these induced magnets, and this is the permanent magnet, Okay, so when you put iron or steel things in the vicinity of permanent magnets, you can induce them like that, and it's easy to know which of the poles will be, because they depend on what side of the permanent magnet they are on. It always goes in opposites. And that's kind of the idea of induced magnetism with a permanent magnet, really. Okay, so in the next video, we'll talk a little bit about more detail about the magnetic fields and the neutral point in the magnetic field, and if we have time, we'll also go into some of the properties of iron and steel. So until then, take care.